Hi, my name is Haley Rial, and I'm the project manager for our delivery team, the Gold Team. For our senior design project, we were tasked with creating a delivery drone. The motivation behind this project comes from the increasing demand for efficient last-mile delivery systems. Traditional delivery methods are often limited by things like traffic and accessibility, and drone technology just provides a faster and more flexible alternative. From a project management perspective, I divided responsibilities across my teammates into different key subsystems, including technical design and integration, structural design, power and electrical systems, and payload mechanism development. We held regular meetings to design reviews to track progress and ensure all subsystems work together effectively and once again within our requirements. This structured approach allowed us to successfully develop and complete a functional drone.
My name is Owen Chastain. I am the mechanical lead for Drone Delivery Team Gold, our senior design project. My main responsibilities included the design and CAD modeling, the physical assembly, the tuning and programming of our software, and I will be piloting the drone as well. When we were first assigned this project, the team did research on different aspects like propulsion, electronics, and materials. We all came together and decided on a light hexacopter design with a servo-actuated pin to release the payload. So after getting a design framework, I started CAD modeling. This was before we knew what our budget was or what kind of equipment we had access to. So the designs we came up with were all purely theoretical. But after we did get our budget and we gained access to UCF's inventory, we needed to refine our design to fit what materials and equipment we could get our hands on. So one of the biggest hurdles we had to overcome was that transition from a theoretical design to real components. Each component had a specific shape, a specific weight, and a specific way that it needs to be fastened onto the frame. All of that needed to be taken into account for our finalized design. Once the hardware was set, we moved into the software integration using ArduPilot and Mission Planner. This wasn't just like a plug-and-play process. We spent a significant amount of time in the ground control station, navigating the parameters list to get the flight logic dialed in to our specific payload.
My name is Evan Kempsey. I am the structures lead for the Drone Delivery Gold Team. My job is to plan and design structural components for our delivery drone. For our drone, we chose a hexacopter configuration because it provides increased lift capacity and structural redundancy during flight. To minimize our total weight, we selected carbon fiber for our primary structural element. The core of the drone consists of two carbon fiber dodecagon plates. We have one on the top and one on the bottom of the drone. Extended from the central hub are 6 carbon fiber arms. They each measure 500 millimeters long and they have a 22 millimeter diameter. To connect these pieces, we custom designed and 3D printed our joints. This includes our knuckle spacers and our motor mounts. For our legs, we have PVC pipes. They're angled at 45-degree angles to help ensure stability upon landing in uneven areas. Using SolidWorks, we had multiple iterations of our 3D printed parts before we came up with our final product. We performed FEA using SolidWorks to simulate the forces the drone will experience. Our analysis revealed a maximum recorded stress of about 15 megapascals alongside a maximum displacement of just 1.25 millimeters. These results give us a high degree of confidence that there is a very low risk of fracture during operation. Ultimately, by combining our lightweight carbon fiber, our custom 3D printed parts, and stress testing, we have engineered an airframe ready to meet the standards of the Drone Delivery Challenge.
My name is David Rickardson, and I'm the Propulsions and Power Lead for the Drone Delivery Gold Team. For our drone, we selected a propulsion system centered around 6 brushless motors. We chose these motors because they offer superior power-to-weight ratio and great durability than brushed alternatives, which is critical for the repeated flight cycles required by Delivery Challenge. To translate this motor power into flight, we paired them with propellers designed to provide a 2-to-1 weight ratio. This ensures that even when carrying a full fast food payload, the drone maintains the maneuverability needed to land precisely within the target zone. Powering these motors in a lithium polymer battery system, we selected this battery system because it provides a high current burst necessary for takeoff while remaining lightweight enough to satisfy our structural weight constraints. By using the performance modeling and propulsion testing, we adjusted our electronic speed controllers, also known as the ESCs, settings to fine-tune the throttle response. Our analysis confirmed that our power distribution system can deliver approximately 20 newtons of thrust per motor at peak efficiency. This data gives us a high degree of confidence that our system can handle the weight of cargo without overheating the battery. We have engineered a propulsion system specifically to address the rigor of the drone deliveries challenge. This is achieved through the integration of high-torque brushless motors, the LiPo power sources, and a modular energy management system.
I'm Ian Ottinger, and I'm the payload and deliveries lead. I'm tasked with designing a payload as well as delivery mechanism used to drop it. For the payload itself, we decided on cat litter to be the actual thing that goes in our container, mainly because you can adjust the weight relatively easily for that, as well as honestly, it's pretty compact, so you can get a pretty large weight in a pretty small space, just keeping it closer to the drone in general. For the payload container, we ended up deciding on bags for that, mainly just because it's lightweight and has a pretty easy way to connect to the device that drops it. It also allows for ease of access to kind of distribute our weight of payload, whether we want to add or take away that cat litter. And it also there's a couple of complications with the handlebars itself. It kind of lowers the payload and lowers that weight a little more. So that's something important to consider when we're actually designing the controls of the drone itself.
During final testing, one of our ESCs failed, which required us to switch from a hexacopter to a quadcopter configuration. This reduced our available thrust and limited our ability to generate sufficient lift, while also making the system more difficult to control. Due to no available replacement hardware, we were not able to restore the full hexacopter configuration. Despite this, we successfully integrated all major subsystems and demonstrated a strong and functional overall design. We are confident that with the full hexacopter configuration restored, our system would meet all performance objectives. This project highlights the potential for drone technology to continue advancing and play a significant role in shaping the future of efficient and reliable delivery systems.